So one of the central principles within lean thinking is that of creating flow, meaning the flow of value to the customer. We want that flow to be uninterrupted, and we want it to be smoothly delivered at a pace that the customer can consume. So this brings into play a couple of important concepts around takt time and line balancing, which we're going to explain in this little segment. Now, the takt time comes from the German word for drum beat. Literally is to do with the baton that a conductor holds when they're conducting an orchestra. Therefore, it's the pace, it's the rhythm, it's the cadence. And in our case, it's the rhythm of supply, the rhythm of production, because that's what we need to hit in order to meet the demand rate from the customer. So takt is dictated by the customer, and it's also driven by the available time we have to produce. So takt time is calculated by taking that available time in a given period. It might be over a shift or over a week. What's the available time for a production, and divided by the average customer demand in that period. So if we take an 8-hour shift, it's the demand within that 8-hour shift. Or if we take over a period of a week, what's the average demand, or the typical demand we need to hit, and therefore we can calculate the pace of production. And of course, there will be different scenarios. There'll be peaks and troughs. There'll be seasonality, perhaps, in that demand. So we need to model those different scenarios and ensure we have the capacity in place to deliver to that demand rate in a smooth fashion. So let's take an example. Let's bring it to life with an example, with a little exercise, and you can try this yourselves, this calculation. So in this situation, we've got 20 work days in a month, and we're running a 2-shift system. The shifts are 8 hours, but we need to net off what's the truly available time for production. So that would mean if we stop for lunch, then we take off that time. If there are designated breaks where we're not running production, we take that time off. And in other situations, if, for example, there were team meetings or there was planned preventive maintenance, we'd net that time off too. So we're just considering the truly available time that production has to hit its numbers. So in this particular case, we have one 30-minute lunch break and 2 15-minute short breaks during every shift. So we can take that off from the 8-hour shift in effect becomes a 7-hour available time per shift for production. And so we can now calculate our total available time over a month and divide that by the number of the pieces required in that month, which in this case is 24,000. So here's the calculation for this particular takt time example. We're going to calculate the time available and then divide that time by the average demand to calculate the takt time. So the time available, well, we've got 20 days, 2 shifts per day, times an 8-hour shift minus the lunch break and the 2 other breaks, which equate to an hour in total, because we have the 8 hours minus 0.5 minus 0.5. So it becomes 20 times 2 times 7. But we also need to convert to seconds. So it'll be times 60 to get to minutes, times 60 to get to seconds. And that gives us a whopping 1,008,000 seconds. So to calculate takt time, I divide the available time by the customer demand. So here goes the 1,008,000 seconds divided by 24,000. And when you multiply that or divide that through, it turns out that the takt time in this case is 42 seconds. So that's the drum beat. That's the cadence we need to hit every shift, every day, in order to keep pace with the customer demand. So we need to design our manufacturing system so that every operation lies just below the 42-second mark in terms of the cycle times, ideally, to create balanced, synchronized flow. So now that we've calculated the takt time, we can start looking at the cycle times within our production process to compare cycle times against those takt times to see where do we have shortfalls in capacity, maybe bottlenecks, or maybe we have excess capacity. In other words, we're looking at the balance of capacity versus demand across the line, across the manufacturing system. And we do this on what's called a line balancing chart. And here's an example of a line balancing chart where, in this case, the takt time is 30 seconds. So that's represented by the horizontal line going across the chart. And then we have 6 production steps from A to F during the manufacturing process. And having calculated the typical or average cycle time for the operator activity within each stage, we're able to compare the bars representing the cycle time against the takt time. And in this case, we can see there are a couple of instances where the cycle time is actually exceeding the takt time. And that's telling us that we don't have the required capacity, that we can only produce at the pace of the slowest operation, which in this case is stage B. We also have other stages, for example, D and F, which have very quick cycle times, which would imply that those operators might have a lot of waiting time because they can only go as fast as, again, the slowest operation. In other words, we've got significant imbalance in the flow in this production system, and we're also unable to meet the customer demand rate, the takt time. So what would you do? How would you adjust to create better balance and better flow? Well, you might say, well, we could add more people into stages B and C. We could buy another machine. We could increase capacity by investing. Well, that may be necessary, but it might be avoidable. Maybe it's better to, first of all, consider, well, are there wasteful steps? Are there losses in some of these stages of production, in particular associated with the bottleneck steps of B and C? So wouldn't it make sense to eliminate the waste and speed up those processes, particularly the slower ones? So the second chart is around eliminating the waste and eliminating the strain in particular on those constraint operations. And you can see now that having eliminated waste, we've reduced the cycle time of all the steps and brought steps B and C to within the takt time. So that's a significant step forward. We can meet the demand rate of the customer. However, we still have significant imbalance in the operational cycle times. So what might you do next? Well, a second or a third step in this, building on that, would be to look at, is it possible to reallocate the workloads across the different operators so that they have a more balanced set of activities? And even, raise the question, do we need 6 operators? It looks like we've got enough capacity here to operate with a reduced number of team members. And so on the third step here, the third slide of this sequence, you can see by reallocating the workload, combining operations, we can hit the takt time, 30 seconds, just about in this case, it is right on the edge, but we can see that it's possible to achieve the takt time with just 3 operators. And now we've got this very closely balanced set of 3 steps that are pretty much got the same cycle time. Now, ideally, you'd want to have some headroom, maybe operating at 80–90% within the takt time to give yourself some flexibility for unexpected losses and fluctuations in demand. But that's the intent here, is first of all, be able to operate within the takt time, and secondly, have a balanced flow of operations, so no one's overburdened or overstrained, and no one has significant waiting time. So we're both effective in achieving the demand, and we're doing it efficiently.